Okay, we're going to start, inshallah. Assalamu alaikum, everyone, uh, and welcome to today's lecture on selected topics on radiation physics. Today, we're going to move to a new topic. Last week, and the week before, or the past two lectures, we talked and covered the interactions of photons with matter. So today, we're going to move to beginning of interactions of particles or charged particles. That's really will be our focus for the next lecture. But today we want to just talk about the collision of two particles. So the general aspects of two particles collision. This is something commonly a problem in nuclear physics and in radiation dosimetry, where we have in such two particles collisions, we have a projectile of a particle with mass m1. Projectile, that means it has a kinetic energy. So that means it has a velocity. And this particle is going to strike or hit a stationary target. So the target by this definition, its velocity is 0, and its mass, it has a different mass than the particle of the projectile. So this is the general aspect. The probability or cross-section for a particular collision, as well as the outcome of such a collision, would depend on many parameters. The physical properties of the projectile, for example, what are the masses of the projectile, what's the mass of the, what's its charge, what's the velocity and its kinetic energy, as well as on the physical properties of the target, its mass and its charge. So this is a basic representation of a two-particle collision. We have a projectile mass with a velocity v1 or kinetic energy, and we have a stationary target with mass m2. And then something happens here when this collision happens, and after that, we might get two other particles or even more. So in this case, we have a particle of m4 with a velocity v4 is scattered or ejected at an angle phi, and we have another particle of m3, mass m3, and velocity of m3 scattered at an angle of theta with respect to the direction of the incident projectile. So general aspects, what are targets usually? What are the targets? So the target could be a whole atom. It could be the nucleus of the atom, or it could be orbital electrons in the atom. As for the projectile, in medical physics, we're interested in heavy charged particles. For example, alpha particles, protons, and heavier ions. For example, carbon ion, so on. We're also interested in projectiles like light charged particles. These are electrons and positrons. And then we're also interested in neutrons. So for heavy charged particles and light charged particles, by their definition or by their name, both of these categories, the particles, they will have a charge. That charge could be a +1 or +2 or any charge, negative or positive. Neutrons, they are chargeless, so their charge is 0. When it comes to heavy charged particles, since they have a charge, they are going to interact through Coulomb interactions. So they will interact with the Coulomb interactions with either the nucleus of the atom. We know that the nucleus has a positive charge, or they will interact with orbital electrons which have a negative charge. Large charged particles, again, their interactions with matter will be through Coulomb interactions. Typical targets are atomic nuclei or orbital electrons, similar to heavy charged particles. Neutrons, they interact through direct collisions. So since they do not have a charge, their interaction is not going to be through Coulomb interactions. Just by their interactions will be just hitting directly the target. And the targets for neutrons are usually the atomic nuclei. Electrons, really, that is not really of a concern. It's very, very negligible. So really, the big concern for neutrons is their interactions with the atomic nuclei. Classification of two particle collisions. So now how we going to categorize two particle collisions? They could be categorized into three groups. Nuclear reactions. Let's see. So the classification of two particle collisions, they're categorized into three groups: nuclear reactions, elastic collisions, and inelastic collisions. So nuclear reactions, basically, we have some physical quantities when this reaction happens that must be conserved. For example, the charge. So if we sum the charge of the particles before the interaction, that should equal to the sum of the charges of particles produced after the interaction. Also, their linear momentum should be conserved, as well as their masses and their energies. The sum of the atomic numbers and the sum of the atomic mass numbers, so that's Z and A, for before and after the collision must also be conserved. So we need to have, essentially what we mean by this is that the number of protons, the total number of protons of the particles before the interaction must equal to the total number of well, Z is just the protons. So after the intercollisions, I'm trying to think of another situation where this is not true when we have these radioactive decays. And also the atomic mass before the collision should also equal to the total mass number after the collision. So the total number of nucleons must be conserved. Elastic scattering. The products after the collision are identical to the products before the collision. In nuclear reactions, the products after the collision might be different than the products before the collision. But when we're talking about elastic scattering, the products after the collision are identical or they are the same as the products before the collision. So if we go back to our diagram here, so if this is representing a elastic scattering interaction, then M4 should equal to M2, for example, and M3 should equal to M1. Also, the total kinetic energy and momentum before the collision are equal to the total kinetic energy and momentum, respectively, after the collision. In general, in elastic scattering, a very small amount of energy or relative energy of the initial kinetic energy of the projectile is transferred to the target. This means that if we go back to this diagram, so if this diagram represents it represents elastic scattering, then the amount of energy that is transferred to the target from this projectile, if it's an elastic scattering, is going to be very, very small, negligible. Essentially, what this means, it means that the kinetic energy of this particle after the collision is essentially going to be very close to the or equal to the initial the kinetic energy of the particle before the interaction. So here, this is the diagram again. So these two particles are the same, and these two particles are the same. So that's for elastic scattering. In elastic scattering, again, we would expect in elastic scattering that the products after the collision should be identical to the products before the collision. Again, M1 equals to M3, and M1, this should be M2 equals to M4. The projectile transfers a portion of its kinetic energy to the target of the form of intrinsic excitation energy in addition to kinetic energy. Means that when this interaction happens, when the particle interacts through an inelastic scattering with the target, it's going to lose energy, but that amount of energy lost is not necessarily gained as kinetic energy by the target, but part of that energy could be transferred to some sort of an excitation energy. So this excitation energy may represent, for example, nuclear excitation. So the nucleus, after the interaction, the nuclear might be excited. So the energy that is transferred from the projectile to the target is part of it, or maybe all of it, is transferred as excitation energy to the nucleus. Could also be presented as atomic excitation or ionization of the target. And most importantly for us is the emission of Brahms-Chaline by the projectile. So when an electron, for example, strikes a nucleus, it can undergo an inelastic scattering, where in this interaction, the electron is going to lose some of its energy or all of it. And part of that energy, or a very small fraction of that energy, is actually transferred as kinetic energy to the nucleus, very negligible, but the rest of that energy that is lost is going to be transferred or going to be emitted as Brahms-Chaline radiation. So this is an example of inelastic scattering. These are examples of heavy charged particles interaction with the nuclei target. For example, it's a direct nuclear reaction. We have here nitrogen-14 hit by a deuterium projectile. We get the outcome from this interaction. We get nitrogen-15 and we get a proton. So this is a nuclear interaction. Notice that M1 does not equal to M3 and M2 does not equal to M4. Two different particles. Elastic scattering, we looked into this when we looked into this when we looked into the Rutherford explained and talked about Rutherford scattering, where in that experiment he had a gold nucleus and we had a source of alpha particles, and the outcome of that interaction was again alpha particles, and the gold nucleus or the gold foil was still there. So this is a representation or an example of elastic Coulomb collision. It's an alpha gold interaction. Finally, in elastic collision, here we have a general form of a nucleus, for example, struck by an alpha particle, and then the alpha particle is scattered, let's say, or loses its energy, part of its energy, and leaving the nucleus excited in an excited state. If it's an excited state, then this nucleus is going to decay by emission, maybe of it will decay through an emission of a photon, a gamma radiation there. So this is a form or an example of a heavy charged particle interaction with nuclei target. Heavy charged particle interactions with orbital electrons. So remember we said that they interact with the nucleus or with the orbital electrons. So with the orbital electrons, this is basically we don't have collisional, we don't have nuclear reactions between a heavy charged particle and an electron. We don't have elastic scattering, or that's negligible elastic scattering between a heavy charged particle and an orbital electron, but we might have an inelastic collision, where in this case, the alpha particle, for example, will give some of its energy to the orbital electron, and this orbital electron can leave the atom, and the atom is left ionized, or it can actually move to a higher energy level, and the atom is going to be excited. So because of that, if we have a vacancy, what's going to happen is the atom will undergo atomic relaxation processes where electrons from higher orbits, they're going to fill the vacancies in the lower orbits and emitting characteristic X-rays or OJ electrons. So this is, again, it's an example of inelastic collision of heavy charged particles with orbital electrons. We have light charged particles interaction with nuclei target. So we have an electron proton interaction or electron neutron interaction. These are examples of what could happen as nuclear interactions. Elastic Coulomb scatter collision. So this is we have it's an interaction with nuclear target. An electron interacts with the nuclear target, and then it gets deflected. And when it gets deflected or scattered, it will be scattered with the same energy, with the same initial energy it had. And no radiation is emitted, no Brahmi is emitted. And finally, we have inelastic collision, where when the electron interacts with the nucleus and it's scattered, then Brahmi radiation is produced in this case. Okay, and this is then called an inelastic collision, because essentially the final energy of the electron or the light charge particle. When I say electron, it could also apply to positrons, by the way. So the final energy of the light charge particle is not going to equal to the initial energy of the light charge particle. And that energy difference is going to be emitted in the form of Brahmi radiation. How about light charge particle interactions with orbital electrons? So we can have elastic Coulomb scattering, where an electron interacts with an orbital electron, and the orbital electron does not take any of that energy, but the projectile electron is going to be deflected with an angle. They're going to be scattered. And this is called this effect, or this is possible at very low kinetic energies for the electron. Usually, if the electron has a higher energy, it's going to transfer some of the energy to the orbital electrons in the atom, and then that will be an inelastic collision. And this effect is called the Ramseur effect. Inelastic collision, this is, I think, by far we all know this, is when an electron an electron or a positron electron interacts with an orbital electron. This can result in atomic excitation or ionization. So these are what we call as hard and soft collisions. We can also have a positron interacting. In addition to interaction with orbital electrons, it can actually undergo annihilation with an orbital electron, and leaving the atom in an ionized state, coinciding with emission of two two annihilation quanta. So the positron, when it annihilates, we will get the two annihilation quanta, but also this annihilation process is going to create a vacancy. And after the annihilation will be followed by also characteristic X-rays. Finally, we look into neutron interactions with nuclei target. So we have nuclear interactions. So the neutron is then going to undergo a nuclear interaction with the nucleus. An example, a very famous example, is cobalt-59, where cobalt-59, it will absorb the nucleus of cobalt-59, or a neutron will be absorbed by the nucleus of cobalt-59, transferring it to cobalt-60 nucleus. And in this process, a gamma photon is emitted. This is not the gamma from the cobalt-60 decay. This is the gamma produced in the process of production of cobalt-60. In nature, we don't have cobalt-60 actually. We have cobalt-59. So what happens is we take the cobalt-59 and we put it inside a nuclear reactor. A nuclear reactor basically has a sea of neutrons. And these neutrons then will start to bombard and interact with cobalt-59 nuclei, converting cobalt-59 into cobalt-60. Another famous also example of interaction of neutrons with nuclei is the fission process. So in fission, a neutron is going to be absorbed by a heavy nuclei. Usually it's uranium, I think uranium-235. And when this happens, then the nucleus, we get uranium-236, and 236 is unstable, and it will undergo a fission decay, producing two heavy nuclei, and also producing neutrons in the process. We can also get gammas and so on. So fission is an example of a neutron interaction with nuclei target. Elastic Coulomb scattering, again, I think this is inelastic, should be inelastic Coulomb scattering. A neutron is absorbed by a nuclei, make it excited. And then once this excited nuclei, then it will emit a gamma photon, decay to the ground state of the nuclei. So let's look at nuclear reactions in more detail. So in nuclear reactions, several quantities needs to be conserved. We said the charge has to be conserved, the mass, and we also need that the momentum and the kinetic energy to be conserved. So let's look at this typical example. Conservation of momentum. This means that the momentum in the system before the interaction must equal to the momentum of the system after the interaction. Since the target is stationary, then its kinetic energy is equal to 0. That means the momentum of the system before the interaction is just going to be given by m1 v1. By the way, this is a classical the classical momentum. After the collision, the m4 will have some velocity, and m3 will have some velocity or kinetic energies, and therefore both of these two particles will have a momentum. So in order to have the momentum to be conserved, we can, for example, set up two equations to define the conservation of momentum along the projectile direction. Let's call this the x-axis, and also momentum perpendicular to the projectile direction. So that's let's call that the y-axis. And what we will get in the x-axis, we will have initial momentum. We have only m1 v1, and then in the x-axis, we have the momentum of particle 3 here, multiplied by cosine of the scattering of this angle theta. And we have also for the momentum of particle 4 multiplied by the cosine of its angle there. So this is angle phi. In the y-axis, we don't have any momentum, initial momentum in the y-axis, so the initial momentum is 0. And then we have, therefore, that we have for M3, the momentum in this direction. This particle should equal to the momentum in this direction for this particle. This means that M3 V3 sine of this angle, theta, minus momentum of particle 4 multiplied by sine of this angle. So the sum of these two momentum should equal to 0. Conservation of energy. Again, we apply the same principles. We look at the total energy of the particles before the interaction. This should equal to the total energy of the interactions after the collisions. So before the collisions, we have the total energy is going to be equal to the rest mass of the projectile plus its kinetic energy. So this is this term here. Plus, we have the rest mass of the target plus 0 because it does not have any kinetic energy, it's stationary. So the sum of these two, this will give me on the left here, this equation, this is the energy of the system before the interaction. Now we look at the energy of the system after the interaction. It's just going to be the sum of the rest masses of particle 3 and 4 plus the kinetic energies of the particles 3 and 4. And this does not necessarily apply to two particles, the products. You can have 3 or 4 particles, it doesn't matter. You just need to always think of conservation of energy and conservation of momentum for the system before the interaction equals to the system after the interaction. Obviously, before the interaction, we just have 2 targets. We have a projectile and we have a target. So we have 2 particles here, and the outcome could be 2 or more particles there. So based on this, we like to define a Q value for the collision. So the Q value is basically, very simply stated, is the masses of the particles before the interaction minus the masses of the particles after the interaction. No kinetic energy is actually there. So this is the Q value. So if this Q value is greater than 1, this means that the collision is exothermic. Exothermic means that when this reaction happens, energy is released from the system. And this energy will be in the form of these kinetic energies, okay, 4 and 3. The sum of these 2 energies, the kinetic energies of the products, is going to be greater than the sum, or greater than the kinetic energy of the projectile. So this is when Q is equal to 0 and energy is released. Now, when Q equals to 0, we say the collision is elastic, meaning that the energies of the particles, the sum of the energies of these 2 particles is going to equal to the energy of the projectile particle. And when the Q value is less than 0, this collision is endothermic, meaning that there is energy, there has to be some energy transferred from the projectile to the target. Or in other words, for exothermic interactions, this interaction cannot happen unless the projectile has some kinetic energy. So if, for example, we can have a very low energy of a projectile particle, let's say a neutron, interacting with a target. The energy is very low, but we get actually the 2 particles here, they will have high energies because Q value in this interaction is exothermic. Now for endothermic, this particle projectile must have a minimum kinetic energy in order for this interaction to happen. So how do we determine this Q value of a nuclear reaction? We can use the masses of the particles before the interaction. We can use the particles, the masses of the particles before the interaction, and the particles of the energies of the particles of after the interaction, and we take the difference. So here's before and after. So take the difference between the two. This will give me the Q value of the nuclear reaction. And if the Q value, as we said, if it's greater than 0, then it's an exothermic, meaning that the nuclear reaction is going to release energy. If Q is equal to 0, then that means it's an elastic, no energy is released. It's an elastic scattering, elastic nuclear reaction. And if it's less, that means that the reaction can only happen if the projectile has a minimum threshold energy. We could also, alternatively, we could use the nuclear binding energies of the system. But we have to just be aware of something, that if we're going to use the nuclear binding energy, then we take the binding energies, or the sum of the binding energies of the particles after the interaction, and then subtract that of the binding energies of the particles before the interaction. So see, it is reversed. Before, after. So using nuclear binding energy, it's going to be after and before. So here is an example. We want to calculate the Q value for the following nuclear reaction. This is an example. We presented this as an example of a nuclear reaction where a deuterium particle strikes a nitrogen-14 nucleus, and then a proton is produced and a neutron-15 nucleus. So these are the values, the atomic mass units of nitrogen-14, nitrogen-15, and deuterium and hydrogen. This data is actually the atomic mass, okay? It's the mass of the atom in terms of atomic mass units. Okay? But in an atom, we know an atom, we have the nucleus, and we have also the electrons. So in order to use this equation, this is actually the masses of the nucleus. So what we need to do, we need to first calculate what's the mass of the nucleus. So to calculate the nuclear masses, we can use that, the nuclear mass equals to the atomic mass minus Z times the masses of the number of electrons in the atom. We just need to convert everything in terms of MeV. So we use that one atomic mass unit equals to 931.5 MeV. And this actually should be electron, M sub E, C squared, this is equals to 0.511 M. So plugging this data into this equation, this will allow us then to calculate what are the nuclear masses of these particles. And here I've done that thing from, this is just calculated from the data of the atomic mass units. Now, there are some tables available where they actually list the nuclear masses for these particles. Here is an example. I looked at a book from Dvorak. So here, for example, he has listed the atomic mass of the particles, and as well as the nuclear mass of the particles. And this data, I believe, they're calculated in the same way. So once we have calculated the nuclear masses, all what we need to do is we need to apply this equation, where these are the masses, nuclear masses before and after. And what we get is we get that the Q value is 8.6 MeV. This means when this interaction happens, we get an energy of 8.6 MeV. That's what it means. It's an exothermic reaction. We could apply the same thing just for demonstration is by using the nuclear binding energies. Notice that we can either you have an access to a table for nuclear binding energies, or you can calculate it actually from nuclear masses. So the binding energy of the nucleus is defined as the rest mass energies of the number of protons plus the rest mass energies of the number of neutrons in the nucleus minus the mass of the nucleus. We know that, for example, if we have a carbon, let's say carbon 12, carbon 12 has 6 protons and 6 neutrons. So if we weigh or the mass of 6 individual protons plus the mass of 6 individual neutrons, we sum that up, and we look at the mass of a carbon-12 nucleus, we will find that the mass of carbon-12 nucleus is actually less than the mass of 6 protons plus 6 neutrons. So that mass difference is converted into binding energy. This is energy required to keep the nucleus together. So using that simple definition, we can then calculate the binding energy, the mass of protons. So this is the number of protons. A minus Z is the number of neutrons, and the mass of neutrons minus the mass of the nucleus. So from this table, from this data, we've calculated here the nuclear binding energies for nitrogen 14, nitrogen 15, deuterium, and then hydrogen. Or this, actually, this is a proton, okay? Because now we have removed actually the electrons, and this is deuterium nucleus. So this is basically a proton-neutron particle. And H, this is a proton in this case. So obviously we have a proton, so there is no binding energy. It's a single particle. So this is 0. But for the other nuclei, we have actually, or these are the data for the nuclear binding energy. So again, we plug in that equation, but we just have to remember that it's after and before. So after, we take nitrogen 15 and the proton, minus before the interaction, this is nitrogen 14 plus the deuterium. And if we do that, again, we get that the Q value is 8.6. This should be an MeV unit here. So again, both methods should give us the Q value of the nuclear reaction. Now, when the Q value is less than 0, we said that there has to be a threshold for this interaction. This interaction cannot occur unless the projectile has at least that kinetic energy. That kinetic energy is called the smallest kinetic energy. We can either define it as the kinetic energy of the projectile, or we can define it as the total energy, the smallest total energy of the projectile. So this is the threshold energies. This actually could be derived from what's called the invariant relationship. I'm sure you have looked into, I mean, you have seen this relationship before. This comes from special relativity, where basically this quantity, E squared, or the total energy squared of the particles minus momentum squared C squared, is invariant. Invariant is different than conserved. Invariant means that it's independent of the reference frame from which we are actually calculating or determining these quantities. So, for example, if we have, let's look at this. So we have a particle, okay, and we have another particle, okay. So this is V equals to 0, and this has some velocity, okay. And then after the interaction, we can get a third particle, okay, and a fourth particle. So this is before and after the interaction. Now, if we were applying the conservation of energy, for example, concept, so the kinetic energies of the particle will depend on the reference plane of the observer. So if, for example, the observer is stationary, this particle will have a certain kinetic energy with respect to the observer. And these particles will have also kinetic energies with respect to the observer, this stationary observer. But now, for example, if we have an observer that is actually moving with a certain velocity, so the kinetic energies for this observer, this particle is no longer stationary. It will have actually a kinetic energy. Its kinetic energy is just going to be in this direction, and this particle will have a lesser kinetic energy in this direction. So again, the kinetic energies of the particle will depend on the velocity of the observer. The nice thing is that if we calculate this quantity, E squared minus P C squared for any system, okay, this quantity does not depend on the observer. So if someone is stationary and is calculating this quantity and someone else is moving with a certain velocity and calculates this quantity, they will get exactly the same quantity. It's invariant. However, if the observer, they calculated the energies of the particles or their momentum, they will not get the same energies. Although the energy could be conserved before and after an interaction, but the point is that the values that they are going to calculate is not the same. Okay? So the nice thing with this invariant relationship is that we can look at the system and select an observer that is stationary, where V of this observer is 0, like the target. And we can have another observer here who is actually going to be this reference plane of this observer will be in the center of mass of the two particles. So the two particles are moving with respect to this observer. The two particles with respect to the center of mass frame will appear they are stationary. So we can apply this concept could be applied in order to determine the threshold of collision. I won't go through the derivation, but it's not that difficult actually. And once that is done, this equation, we get this equation to determine the kinetic energy, the threshold, or the smallest kinetic energy of the projectile in order for the nuclear reaction to happen. It's given by the difference of the final masses squared minus the sum of the final masses squared minus the sum of the initial masses squared or squared divided by 2. This is the target, the mass of the target.
Sorry, Dr. Ramid, if you
Yeah.
allow me to ask a question. So the threshold is not as the same as the binding energy, because I think binding energy is constant for different shells, and we have to reach this amount to do the how to say it, to make the energy. to change the energy.
Okay, binding energies, we have electron binding energies, and we also have nuclear
Atomic
binding
binding energy.
atomic
Yes.
and nuclear. Okay, these are just the energies required to keep the atom in that state. So when we have an
Yes. So
atom, so these are binding energies. I'm not talking about this. Now we're talking about collisions of two particles. I have a target, okay, and I have a projectile. I have, for example, I have, let's say, a lead atom, and I have, for example, a proton, okay?
yes. Yes.
And there is going to be a nuclear reaction. The question is, can this nuclear reaction happen? And if, or does it need, for example, the proton needs to have a minimum kinetic energy in order for the nuclear reaction to happen. So the first thing we do is we calculate the Q value of this interaction. I don't know what, for example, are the outcomes.
But if I can clarify my question, Doctor. So the binding energy inside the nucleus is constant.
True.
So the threshold to happen has to be equal to some energy above this constant. Did you get what I mean?
You mean just to knock out, but what about if we want to knock out two particles?
So, so the energy has to be double.
So we have to calculate, we have to know what is the outcome of the interaction.
Okay, I understand.
Okay.
Thank you, Doctor.
It's not just for one particle, not like, okay, the energy required to knock, for example, a proton or a neutron from the nucleus. It's true. What you're saying makes sense. Okay, we have to at least give that amount of energy. I agree with you. But we're talking here about something more general. We're talking about, okay, if this nuclear reaction is going to happen, for example, an alpha particle is going to be emitted from the nucleus. For example, that's the nuclear reaction. We want to calculate what is the threshold then for this nuclear reaction to happen. So,
I understand. Thank you,
okay.
Doctor.
Okay.
Thank you.
So again, we want to calculate what's the threshold kinetic energy of this nuclear reaction. But remember, the reaction we had here in our example, we had nitrogen 14, deuterium, proton, nitrogen 15. This we calculated to be an exothermic interaction. So actually no threshold is required. We just bring this deuterium close to the nucleus of nitrogen 14, and this interaction will happen. And we get this Q value. But the reverse interaction, the reverse nuclear reaction, that's going to be an endothermic. So here, and my question is, we want to do the reverse interaction. So proton hitting a nitrogen 15, and we get neutron nitrogen 14 plus a deuterium particle. This is going to be an endothermic reaction, nuclear reaction. Make sense? It's the opposite. It's the reverse.
Yes, it makes sense.
Yeah. So here, this Q value is positive. The reverse reaction is the Q value is negative. So there has to be a threshold energy. So again, we plug in this data, and we get that, okay, the kinetic energy of this proton has to be 68 MeV, at least 68 MeV, in order for this reaction to occur. Okay? So this is the minimum kinetic energy of the proton for the reaction to occur. We can always check any nuclear reactions. Check, for example, are they exothermic or endothermic, by just calculating the Q values. And then if the Q value happens to be negative, then we can also take this further and say, okay, then what should be the energy of the projectile particle in order for this interaction to happen? So we can then apply this formula for the threshold energy. This threshold energy is actually how we derive actually the nuclear pair production formula, the threshold for nuclear pair production. So here in nuclear pair production, this, if we look at this, so the formula states that this is the threshold, okay, equals to I think this is the products. So this is we'll call this M after okay, squared minus the sum of M before, okay, squared, and of course there is a C squared somewhere there, and then we have the 2M. This is the target, so this will be the target, and then C squared. So in nuclear pair production, what do we have? We have a photon with energy, and we have a nucleus. And what happens after the interaction? The nucleus remains the same, no change, and then we get an electron and a positron pair. So this is some sort of a nuclear reaction. So then how do we calculate what is the threshold? We all know that threshold has to be greater than 1.022 MeV. But we can use this formula to actually, or actually based on this formula, this is how the threshold energy is calculated. So we apply this equation. So this is the energy of the photon threshold, okay, equals to the mass of the particles after, whatever we have the system here after. So we have here, this is the mass of the target plus 2mEc squared. These are the masses of the two. And then this is the square minus, before the interaction, the photon does not have a mass. So here we have, this is the M of the target squared. Here we need, since I'm putting C squared, I need to put this divided by the mass of the target C squared. So again, you can, this is now becomes a mathematical problem. And when you do, we get from here, H threshold equals to, we get 2 MeC squared and target C squared plus we get 4 MeC squared whole squared divided by of the target C squared and get 2. So this 2 cancel with this. This is 1. We get 2 here, and we can take MEC squared or 2 MEC squared outside. There's something I did wrong, or we get here 2 MEC squared plus we have here MB plus we have 2 MEC squared. There's something wrong. Something wrong here. I cannot figure this out. But anyway, the point is, once you do this, you have to sit down and do it properly. Once you do this, actually, I think it's correct. Yes, I think it's correct. The formula is correct. Once you do this, you will get this formula here: 1 plus ME divided by the mass of the nucleus, the mass of the target. Remember, we took the ME and then we divide by the mass of the target. We should get this formula here. Or we divide by, yes. So this is how the nuclear pair production threshold for nuclear pair production In general, the mass of the target is much more than the mass of an electron. This is why this ratio is usually negligible. We ignore it. So if we talk about hydrogen, the mass of a proton is 938.3, and the mass of an electron is 0.5. So the ratio of these two is roughly around 2,000. So this is 1 over 2,000. So again, that's mean that the nuclear pair production can be approximated as a 2 MEC squared. If the target is even larger than hydrogen, this is going to be even more massive, and this ratio is going to be even smaller, and so on. Now, for electronic pair production, so it's the same thing, but now instead of the target is going to be an electron. So all what we do is this the target, we replace this by an electron, we get here equals to 1, 1 plus 1, and we get here that the threshold for triplet production to happen is going to be 4 MEC squared. So we're going back. What's really interesting for us is not really this when we talked about where is this equation is after. I thought I had it somewhere. Let me go back and just. I thought I had a slide for that, but anyway. Conservation of energy to time. Okay. There is a general equation of, oh, here it is. Okay. Okay, these two slides, they're reversed. So we can actually derive the general energy transfer. Now what we're interested in, we have a projectile, and we want to know how much of that projectile, how much energy is going to be lost by that projectile when we have an elastic or a classical scattering. Elastic scattering. So this is what delta E represents, is that the amount of energy lost by the projectile. This is the general expression. It will depend on the angle, scattering angles of why we have this here. Someone actually annotated. So this amount of energy that is going to be lost by the projectile will depend on the energy of the particle, the projectile particle, multiplied by this ratio of masses, multiplied by the angle, the scattering angle, okay, squared. In a head-on collision, so if the projectile is directly hitting the target, we expect that the target and the projectile will still continue in the same along the same line. In other words, if we look at this figure, here, this is an impact parameter. We have an impact parameter. This is an impact parameter. Okay. Now imagine if this is hitting, it's a head-on collision. This is hitting directly the target, the impact parameter is 0. We would expect that this particle and this particle to be along this line. They're going to be along this line. Okay. And that will represent the maximum actually energy transfer. Or in a head collision. So in a head collision, when this phi equals to 0, then we have a head-on collision, and that will represent the maximum energy transfer. Or in other words, we want what's the maximum possible value of this delta EK? Is maximum when cosine squared of the cosine squared of phi is equals to 1. And that will give us the head-on collision. It depends on the energy of the particle, plus some masses here. So this is the maximum energy transfer. is given by this ratio, product of the masses and the sum of the masses. Here we have a 4, here we have a square, multiplied by the energy of the particle, of the projectile particle. And the momentum transfer, also we can derive it. It's given by this formula. It depends also on the masses of the two particles, as well as on the momentum of the projectile. So let's look at some special cases. Special case 1 is when M1, when the mass of the projectile is much larger than the mass of the target. An example would be, for example, we have an alpha particle or a proton hitting an electron. So what is then the maximum energy transfer from the proton or from the alpha particle to this electron? This roughly will be given, since M1 is much larger than M2. So this is much larger than, or we can put it here. This is much larger. This M1 is much larger than M2. So M2 then is 0 compared to M1, and then M1 divided by, we have here M1 squared. So one of the M's, M1 will cancel out with M1 here, and we get the ratio of M2 divided by M1. So in this case, the maximum energy, possible energy transfer is going to equal to 4 M2 divided by M1. So let's look at, for an example of a proton hitting an electron. M2 is the electron, because the electron now is the target. Electron is the target, and proton is M1. This ratio is 1 over 2,000. So this is 1 over 500, then it will be roughly. So in a head-on collision of a proton with an electron, then about 1 over 500 of the proton energy is going to be transferred to the electron. A very, very small amount of this energy is in fact going to be transferred to this electron. Let's look at the other case. The other case is when M1 is much smaller than M2. So we have an electron hitting a proton. The proton is the target and the electron is the projectile. So everything is reversed. So here we have M1 over M2. Okay, so the change in maximum energy change is going to be, it could be very high. So a lot of the energy, or actually there is something, I'm trying to think of something here. If this is much larger, yeah, again, it's a square. So actually, it should be actually a very small energy also be transferred there. But anyway, it's given by the same formula, but these two are reversed now. M2, sorry, it's fine. Now I get it. M1 is the electron. So M1, this is 0.511, and M2 now is the proton. So again, this is roughly around 2,000, about 2,000. So the ratio of the two multiplied by 4, I think it's 250, right? It's here. This ratio is 2,000, 1 over 2,000 multiplied by 4. No, sorry. Mass of an electron is 0.5, and the mass of proton is roughly 2,000. So this ratio is going to be 4,000. 4 over 4,000, this is like 1 over 1,000. So it's even actually even smaller. And here we have the same thing. The mass of an electron, the mass of proton, this ratio. Now I'm confused, okay? The mass of an electron is, this is 0.511. And the mass of proton, this is 938.3. So the ratio of the two is 1 over 2,000, roughly 1 over 2,000. Okay, that makes sense. So the ratio of the two particles, the mass of the two particles is 1 over 2,000. So in the first case, the projectile was a proton, and the target is an electron, this ratio is 1 over 2000. 4 over 1 over 2000, this is 500, so 1 over 500. In the second case, the projectile is an electron, that's the particle that has a kinetic energy, and the target is the proton. And again, this ratio is 1 over 2000 multiplied by 4. Again, we get the same thing. So it doesn't matter whether we have an electron hitting a proton or a proton hitting an electron. The ratio the fraction of the kinetic energy that is going to be transferred is 1 over 5,000. When we have M1 equals to M2, remember we're talking about elastic scattering, so the masses we don't have M3 and M4. All what you need to consider is M1 and M2. When we have mass M1 equals to M2, then the maximum energy transfer, this is just going to be equal to the kinetic energy of the particle. An example of this would be we have a proton, we have a positron and an electron. So positron, electron, the max, so imagine the positron has a kinetic energy, let's say 1 MeV. It goes and hits a head-on collision with an electron. The energy that is transferred, the maximum energy transferred to the electron is going to be the kinetic energy of the positron is going to be 1 MeV. And this is the case when we can distinguish the two particles. But if we cannot distinguish the two particles, the two particles are indistinguishable. So an example would be an electron scattering, head-on collision. Elastic scattering through a head-on collision. Then the maximum energy transfer in this case is going to be half of the kinetic energy. The reason is we don't know the particle that because we cannot distinguish between the two particles. Or after the collision, we're going to still see two particles. We cannot know what the particle, let's say A, is it the projectile or is it the target? We cannot distinguish between the two. So the maximum possible energy transfer is this going to be 1/2 of the kinetic energy of the projectile. Now, these equations that I presented to you, these were actually for based on classical momentum and energy. Now, if you could use actually relativistic, but then the formulas, they're not as big. So the formula, for example, the maximum energy transfer, when we're talking about relativistic range, this is given by this horrible fraction here. It's a much larger there. And the maximum momentum transfer, again, it is given by this factor here. This is the initial momentum of the projectile, and this is the factor by how much the fraction of this momentum is actually going to be transferred. But what we expect is that we can, if we look at, or the limit of these formulas as the velocities are non-relativistic, they should be exactly similar to those that are derived based on classical derivation. So notice that when we're doing with electrons, usually, so the electron with energies, let's say at 1 MeV, an electron at 1 MeV range, this is actually a relativistic range for the electron. And then more appropriately is to calculate the energy transferred using the relativistic formulas rather than the classical formulas. But if we're dealing with a proton, for example, with an energy of, let's say, 1 or 10 MeV, 10 MeV proton, that is still classical, is a good approximation because its speed is not yet in the relativistic range. So again, these are the special cases using these relativistic formulas. When M1 is much greater than M2, this is the maximum energy transfer that's given by this formula here. And again, when I expect that when we convert or take the limit of these expressions to the classical case, so when gamma is very close to 1, then probably we're going to retrieve back the relativistic, the classical relationships. And this is the case for M1 much less than M2. This is the formula. But however, when we're talking about M1 equals to M2, still the maximum energy transfer, they're the same. It's just going to be the kinetic energy if we have distinguishable particles, and is going to be equal to one half of the kinetic energy when we have indistinguishable particles. Okay, so this is the last slide I have for today, for our lecture today. Next lecture, I needed to talk about this because next lecture we're going to look into stopping powers, interaction of, especially going to look into interactions of charged particles with matter. We have soft collisions, we have hard collisions, and Bremsstrahlung, and then we're going to look into the stopping powers. So we have collisional stopping powers, we have unrestricted collisional stopping powers, we have restricted collisional stopping powers, and we have radiative stopping powers. So I felt this lecture is just a very good introduction to at least how charged particles interact. But the quantities of interest definitely will be in the next lecture for stopping powers. Okay, any questions? Still trying to figure out why this formula, something is wrong with the formula I had. It is 4. Let me see square. There is a 2, there is a factor of 2 that I'm missing. It's not working out. Anyway, yeah, there is a factor of 2. I don't know why there is a factor of 2 in the formula that I'm missing in the formula. But anyway, are there any questions? So in brief, we said charged particle interactions. We have nuclear reactions, we have elastic scattering, and we have inelastic scattering. We looked into, for example, how to calculate a Q value for, when we talked about nuclear reactions, the Q value for a nuclear reaction. We also looked into threshold. So we can calculate this on these formulas, determine if this interaction is to happen, so this is when we have an endothermic nuclear reactions. What is the minimum kinetic energy required by the projectile in order for this nuclear reaction to happen? Okay, any questions?
I do have a question,
Okay,
but it's in a different topic. I don't know
fine,
if I should ask
no
you here or
problem.
not.
Let me stop the recording. Okay, so I'm going to stop the recording.